So let me just remind you that last time we invested quite an effort in understanding how to calculate the ensemble average of the general object of the following type. Just we have product of several I put index f here, several characteristic polynomials of a random matrix in the numerator, product of characteristic polynomials or inverse spectral determinants with in general different parameters in the denominator, and we quite generally demonstrated how to perform this averaging explicitly, and this is I think I call it omega of all these z's arranged in terms of diagonal matrix. How to calculate this object, or better to say represent it, using operations with commuting and anti-commuting variables, these supercalculus rules of which we discussed. And we arrived to a compact expression amenable to saddle point evaluation in large n limit using this variant of superbosonization technique. Today, and we just stopped short of introducing, or performing this, or at least discussing this asymptotic analysis n to infinity, and just calculating, at least in some non-trivial case, this type of object explicitly. I will, in the first half of my today lecture, I will perform such an analysis for the simplest non-trivial object, which my choice of the correlation function of this sort to calculate is as follows. It's written here. One can make the minimal choice should be two determinants with opposite signs of imaginary part of their spectral variables in the numerator. In the numerator, it's less important to have opposite sign of imaginary parts. You can have whatever you wish, but in the denominator, you really, to have something non-trivial, as we remember, to have this hyperbolic symmetry play an important role, you need to have imaginary parts of these two parameters different. I make an even simpler choice. I take these spectral parameters in the numerator to be complex conjugate numbers, and again, different complex conjugate numbers in denominator. I like this object very much. In fact, it's not very frequently I don't think that you find a lot of discussion of this object even in random matrix literature, but I like it very much. I can explain you about what reason. It's also nice for illustration, but just without going into any detail, I'll tell you that if you like to calculate, you remember we all love resolvents, and in the end of the day, we are mainly interested in resolvents or green functions. So suppose you have your green function is a function of parameter z, namely which is a matrix element of our resolvent taken a diagonal element of the resolvent. Then my claim is that if H is taken from Gaussian unitary ensemble, one can relate the joint probability density of real and imaginary part So even not an expectation, but joint probability density of real and imaginary part of this important object. We will see importance of this object later on, and also importance of considering distributions of these quantities, not only expectation values, later on, when I hope we will be able to discuss localization. But even at the level of random metric theory, it's interesting object, not frequently discussed in the literature, although some results are available. And my claim is that a very simple calculation, for those of you who will be interested afterwards, I can show this. One can show that this function in fact is directly related to Laplace transform of that joint probability density. So it's really also a meaningful object. But for us, it's just one of possible object of interest, which I'd like to show how to calculate explicitly using this supersymmetry technique. I will use a version of supermatrix version of Scheffer-Wegener method, rather a superpositionization here. I just find it slightly more convenient, but of course you can go any route. So let me remind you that Scheffer-Wegener method is basically it's all based on this identity. We discussed at length and in detail why it's important and convenient tool using its so-called bosonic version. But here this is the only thing we need, because we remember that we basically in Fermi-Fermi block we won't have any essential problems of convergency when interchanging limits, because essentially Fermi-Fermi block comes from representation of product of determinants, and boson-boson block from inverse. So really all problems of convergency and non-trivial hyperbolic symmetry are here. So our discussion and knowledge of Scheffer-Wegener parameterization that we already have suffices for our goals. So I here just give explicit description of this parameterization in terms of supermatrices. I call them Q lambda, because with a good reason we remember that in Scheffer-Wegener method there is free parameter, positive parameter lambda, which we make use of just tuning to correct saddle point in the end of the story. But on the level of parameterization, this is free parameter. Q is supermatrix, consists of, as usual, of boson-boson, boson-fermion, fermion-boson, and fermion-fermion blocks. Boson-boson, fermion-fermion blocks are made of commuting variables, and these blocks, 2 by 2 blocks, made of Grassmann entries, matrix entries. The structure of boson-boson block is precisely the structure we had, just literally copied from our discussion of Scheffer-Wegener parameterization in the case when we had only inverse determinants. Fermion-Fermion block, we use imaginary unity. Okay, here it's minus I, but minus is should be convenient to put it here. Important thing is I times Hermitian matrix. We remember why we need this I. This is just to remind you that when we consider Gaussian integrals which have super trace q squared in the exponential, then to have this Gaussian integral well defined, we need this I to have corresponding expression positively defined. We need this I, and this is related with definition of supertrace. Now, as I mentioned, boson-fermion, fermion-boson blocks just consist of each of 4 Grassmann variables, and the measure is just product of all independent degrees of differentials of all independent degrees of freedom. These p's, which are positive here, I take minus sign here, so they are both positive. And all differentials entering here, two real numbers, and then the real part, the imaginary part here. Tau is a complex number, so d tau bar means real and imaginary part again, and product of all differentials of Grassmannians. And just useful exercise, but this basically amounts to looking at our explicit calculation for the old case, when we had only inverse determinants, and then I showed that this variant of Hubbard-Startonovich transformation holds. Basically, here it's just small decoration of that calculation, and you may check that this gives such a formula that I will use later on. Now we follow standard procedure. We represent each of these determinants in the numerator as Gaussian integrals of anti-commuting variables. We represent those in denominator as integrals over commuting variables. We perform the disorder average precisely in the way shown in the previous lecture. And then we have a term which is quartic in all in components of Grassmann variables and all Grassmann vectors and usual complex vectors. We linearize it using this representation. Please recall R is matrix. I won't write it in the full, but remember this was matrix bilinear in these components. It was, I think it was written in the following way, then something like phi, psi, psi, phi, and here it was, I think, minus psi, psi, if I remember correctly. You can find it in your lecture notes in the previous lecture. So this is our supermatrix R. Supermatrix R. And we then, again, we linearize in the expression in exponent. So now we have this form. It's bilinear, it's linear in R, therefore just quadratic in components of phi. So we see that we can perform integration of this in the same way as we always do when we apply Hubbard-Startonovich transformation. We perform corresponding Gaussian integrals exactly. And here, again, Schaeffer-Wagner parameterization for Q takes care of the fact that corresponding integral will be well-defined, convergent. This was the problem, if you remember. Okay, I'll leave it here. If you remember, this is always the problem due to presence of hyperbolic symmetry behind. We need, just before performing that integral, let us consider in more detail structure of this term. It's written here, it's just repeated here. It can be written down as a scalar product of supervector phi. You see, I use for phi the following. It consists of 4 sub-vectors, I would say. So first two made of 2 phi's used to represent denominator, these two determinants in the denominator as Gaussian integrals, and the 2 psi's come from similar representation of 2 determinants in the numerator. So we arrange them in this composite object that we called supervector. I will frequently refer, and everybody does, at least in physical literature, to these 2 components as bosonic and to these as fermionic. And matrix, basically matrix which define this quadratic form, it's of the following sort. It's supermatrix, but it has 2 by 2. But every element here, okay, S times Q, or even Q itself has this structure. So QBB has it's just 2 by 2 matrix, right? So what I mean by this notation, that just every entry of this matrix is multiplied with identity matrix of dimension n. So this is a matrix of dimension 4n, as it should be, because it multiplies vector of length 4n. But it's very simple structure. Yes?
Sorry, could you again say why you chose ZF2 to be, so this different ZFs not to be independent, but rather complex conjugated?
It's just one of possible. Okay, they must have opposite signs of imaginary parts. But I could take here, say, arbitrary, real part arbitrary, here also real part arbitrary, but also imaginary part arbitrary, but opposite in sign. This will be general object. This is the simplest one, which I, okay, first of all, it's really the simplest meaningful object, and both terms are relevant. It's simplest and meaningful. I know its meaning. But even without that meaning, you just can consider this as a useful exercise of evaluation. This you are not obliged to know. I'd like to show, at least on one particular simplest chosen, judiciously chosen case, how to perform this calculation to the very end, to derive a zero-dimensional linear model and actually evaluate the value of this integral as a function of very relevant variables.
Yeah, but with this choice, what kind of correlation functions could you evaluate, for example?
I told you. Okay, I do not have time. It's exercise of maybe 20 minutes or maybe less, but I do not have time. Just be assured that if you know this object and you know that your matrices are from GUE, you can recover the joint probability density of real and imaginary part of this object. Yeah, this is precisely the object. It's one of. That's why I like it that much. But without even any meaning, it's a legitimate object, and let us try to evaluate it. It's interesting object in random matrix theory. Okay. You were afraid that it's too simple. This was that it's too simple, contains no information. Yes. Be sure that's not the case. It cannot be. It cannot be too simple technically because it already has all a structure. It has opposite signs of imaginary parts in the denominator, so it will have full hyperbolic symmetry plane role behind it. So okay, but it so happens that it also has direct meaning in random matrix theory. Okay, now we can, with knowledge of this structure, we just perform this explicitly, the super integral. We know that when we perform Gaussian integral over supervector, we get inverse superdeterminant, and here, because of this structure in this space of dimension n, just proportional to unity matrix, we will have this superdeterminant raised to power minus n, which is nice because we have this parameter in here exponentiating. This term, we will see that we have the form that we always liked, exponential, big parameter times some function, and therefore this integral can be evaluated by saddle point method. Now, to elucidate the reduction to supermatrix sigma model, let us even further simplify, probably to your disgust. Let us put even real parts equal to 0, still it's meaningful object, as long as we keep these two complex conjugate. So it's enough just to tell what is the imaginary part. And I hope you remember that all interesting life, so to say, in this object was expected on the scale when imaginary parts are of order of basically inverse size of the matrix. We remember that in this case we really had a manifold of saddle points which non-trivially contributed to our integral, or basically this is the notion of nonlinear sigma model. So technically how it happens, we assume, we just introduce these ethers with scaled versions of imaginary parts, just explicitly having this scale factor 1 over n in front. And I just massage a little bit in the way we already did, in fact. So it's not needed to be discussed. It just I write superdeterminant minus n as exponential minus n supertrace log, expand everything using small parameter 1 over n, and collect leading order terms. And I see that basically it will have superdeterminant raised to power minus n of matrix Q, and exponential of supertrace, this parameter eta. What is eta? Eta is a matrix now. It's diagonal matrix which contains eta b's and eta f's with important thing, with their corresponding signs. And we see that these minus signs here and minus sign there. So so that's what we have. Now putting this back to our integral, we see that in the large n limit we need to consider the following integral. Now our scaling ensured that this term does not have any longer this parameter n in front, so it's in the sense of order 1 when we perform large n limit, or in different terms, it won't modify our search and exploitation of saddle points. So we need to find stationary points of this expression. Its trivial variation gives that matrix Q lambda at the saddle point should satisfy just Q plus inverse of Q equal to 0, which means that Q squared equal to minus 1. I mean, this is again this simple relation is just ensured by this judicious choice. If I kept real part of z to be something non-zero, I would have then these semicircular densities coming in various places. I wanted to get rid of it, so I just took z equals basically real part equals 0, and then really saddle point is the most simple thing. It's just matrix squared equal to minus 1.
Question. Wouldn't variation just yield the supertrace of this expression to be 0?
No, because if you vary something on the sign of supertrace, you will get equation matrix for matrix, not for supertrace. But okay, this I leave it for you to exercise to check it. You do not need supertrace. You can say trace. Just remember our practically identical equation for usual variable. Just to check that if you vary something on a sign of trace, you will get a matrix equation for the matrix itself.
You want to vary all the matrix elements?
Yes.
Q.
And you will get supertrace of some object times variation of Q equal to 0 for any Q, for any variation, and this ensures that your matrix will. So this is a real equation for the matrix. And solution is just, okay, here's minus 1, so it's minus imaginary unity, and then any invertible matrix times any matrix whose entries, diagonal matrix with entries plus or minus 1 in all combinations, and inverse of invertible matrix. But we encountered, I won't go through all these analysis that we separately did for analyzing bosonic and fermionic sector, because now this analysis just combines. And we remember that in bosonic sector we should take appropriate saddle point and see which one is reachable by playing with this parameter lambda, and we know what is the choice. And in fermionic sector, we in fact should ensure that it gives maximal contribution. We also discussed it. So in the end of the day, just recalling that analysis, we will see that the maximal contribution comes from the following choice. Just matrix sigma is the same as our matrix S, and explicitly it's diagonal 1 minus 1, where here are okay, this is supermatrix, right? So it has a diagonal supermatrix. So it has boson-boson and fermion-fermion blocks, and boson-fermion-fermion boson blocks are 0. Still it's supermatrix. So in boson-boson block we have 1 minus 1. In fermion-fermion block we have 1 minus 1. Simple matrix. Now, however, this ordering first two bosons and then two fermions, it's standard and convenient when you just discuss supermatrices and their superstructure. But it's inconvenient if you'd like to write explicitly parameterization for these matrices T. It's much easier if you just rearrange these entries in the following way. You arrange them in the following way. You first arrange these two and call them, okay, it would be appropriate to call them probably B1, F1, and then B2, F2. Bosonic, fermionic, bosonic, fermionic. Still it's supermatrix, but just reshuffling its rows and columns. It's just that in this representation it's natural and most convenient, most explicit, I would say, to write down a parameterization for matrices T, which we know they live on a particular manifold. And this is a parameterization we use. In fact, something very similar we've seen in Andreas Ludwig's lecture when he considered parameterization of unitary matrices. It's not surprising, not coincidence, because basically what he said, as far as I remember, that this is just kind of sines and cosines. Here we will have we remember that we have a compact symmetry like a sphere in some sense in fermion-fermion block. So really there will be signs of the type sine and cosine. But in boson-boson block we remember that rather we will have sinh and cosh. We will have hyperbolic functions because of that hyperbolic symmetry. And we discussed that quite a few times. So explicitly, we combine these two features, and explicit parameterization for T is still in the same form that we had before. But now T's are 2 by 2 supermatrices. They have 2 by 2 supermatrices. So in T12 and T21, they have independent degrees of freedom. Basically, these bars, as we remember, should be understood just as independent Grassmann variables. And TB and TF are commuting variables with the only restriction that the modulus of TF is smaller than 1. And this is, in fact, we remember that this part comes from fermion-fermion block, so it's really something like cosine. Whereas for TB, or rather, probably here it's not cosine, but sine. I use it sine. So this is sine, this is cosine, or it's hyperbolic sine and hyperbolic cosine otherwise in boson-boson block. So we do not have any restriction on TB because hyperbolic sine can go wherever it wants. Now alphas, betas, Grassmannian, as I discussed, and corresponding saddle point. If we just put, we remember that the saddle point manifold will be given just by T, this matrix. Okay, if we this sigma rearranged in U notation is just 1 minus 1, where by 1 we understand identity matrix of dimension 2, so 1 minus 1 in this sense. Oh, here it definitely should be inverse of T. Here is please correct in your notes. Here is inverse of T. And should be clear from here, because the only thing which I did, I made particular choice of sigma with that signature. So it's just, of course, this inverse of T just carries over here. And again, you can get explicit expression for entries of Q matrix, which parameterizes your saddle point manifold. In terms of these T's, it's useful exercise. Multiply T 1 minus 1 inverse of T, and you will get this. It's easy exercise. And just for your information, I should provide a measure to integrate, invariant measure on this manifold. And this is it's very pleasant feature of this particular model with this particular symmetry class that we started from Hermitian matrix. That invariant measure in this representation is very simple. It's just dt1 to d21, where t12 and t21 are just all independent differentials here. And this is, one can show that this is invariant measure on this manifold. So after all these preparation and explanations, here comes our first supermatrix nonlinear sigma model. Still, it's so-called zero-dimensional version of it. It means, I think that Andreas all the time alluded to kind of effective spins which live on some, basically on some manifold. This is, if you'd like, a kind of spin. If it would be only the sphere which we parameterize in fermionic block, it would be really something like a spin going in this sphere. We have also this non-compact part of this spin because we have essentially the structure is direct product of a sphere with hyperboloid. So it's more complicated than that, but still it's something of this sort. And this square root structure reminds us all the time of this. So this is the simplest possible version of nonlinear sigma model. And on the other hand, it's nothing else but scaling limit of our object. I mean, this ratio of two determinants in the numerator and denominator. I mean, particular case for this object when only two exist, and also with particular choice of spectral parameters. What remains of spectral parameters are the imaginary part entering here. In new arrangement, they just with plus here and with minus here. And let us calculate this integral. We many times arrive to this stage for bosonic, only boson-boson sigma type of nonlinear sigma model, or better to say to hyperbolic nonlinear sigma model purely, to its compact version. Now it's supersymmetric version or supermatrix version. And let us perform this calculation to see parameterizations for Q. You see that we have a parameterization, so just go on and calculate. But it's not that easy, although it's very explicit, it's not that easy. And where is the difficulty? Difficulty comes from these square roots. Square roots are not pleasant things to deal with. Although I believe it should be possible, but there is a convenient way suggested by Yefetov to change to more convenient set of variables. And what is this convenient set of variables? You see, if you have two complex matrices, just forget about supermatrices. But if you have two complex matrices, you always can go to so-called singular eigenvalue. If you have, say, complex matrix T and say you have its Hermitian conjugate, you can consider eigenvalues of, say, of their product, and these are so-called singular values. And this allows to parameterize T and T Hermitian conjugate of T in terms of these singular values and corresponding pair of unitary matrices. So a very similar construction is employed here, although it's decorated with these Grassmann variables, and also one of these measures. Okay, I won't. Martin does not like the notion of unitarity, obviously, if he does not like of the notion of this involution. But we do not need it. It's just a pair of matrices made, which are built from Grassmann variables, and one can show that indeed it's very close to basically straightforward extension of this idea of singular value decomposition. And one can parameterize this T12 and T21 using two matrices U and V, which are made of new Grassmann variables in this way. And
can I?
Yes?
Since you giving me sort of the key here by bringing up Unitarian hermiticity. So let me shock you a little bit.
Yeah.
Let me shock everyone. Go back to that formula in the middle for Q, where the inverse is missing. And then comes this matrix, T1, 2, T2, 1, and so on.
This one.
Right.
Uh-huh.
We like this for the nice form of the diagonal box. It's just quadratic. And we know how to do Gaussian integrals and things like this. We also like it because the integration form or integration measure is just the simplest possible one. It's the product of differentials of the commuting variables and the product of the derivatives in the anti-commuting variables. It couldn't possibly be any simpler. The only thing we don't like are these square roots on the off diagonal. We have to expand them or do something, and then we get a series, and things are messy. However, there's a recent suggestion by two young Russians, Ivanov and Skvortsov, who say, let's just move one square root to the other side, and then say the square root on the left lower block to the right upper block, and then in the left lower block we just have linear T21. On the right upper block we have linear plus cubic. And this is possible to do, and that is the best possible choice you can make. No square roots, just linear plus cubic. It's called Dyson-Maliev.
Yes. And I'm pleased to say that Maliev is the person who was one of my PhD advisors, or at least partly my PhD advisor.
Of course, you can only do this if you don't insist on Hermitian and things like this. You're breaking Hermitism. So anyway, and that's the simplest way to do this integral, not the Fyodorov one.
Yes, I agree, but I'm not shocked because we already discussed. But really, this is an interesting suggestion. This just shows that there are many ways of deforming, on looking on these manifolds and deforming them in all possible ways to calculate these integrals. Historically, I think, although, that effect of parameterization played a very important role in doing all these things manageable in calculation. I don't think that you disagree.
Historical, but usually the first idea wasn't the best one. Usually later people come up and clean up
Yes, I agree
the
with this.
story and find the optimal formulation.
That's correct. Yes, but still, I think it deserves to be presented in some way. But maybe next time in the lecture I will present already Skvortsov and Ivanov method.
Sorry. How do you actually do this moving of the square root? It's a similarity transformation?
Not quite.
Or a deformation of the...
Deformation.
You should imagine that you have to remember the Cauchy theorem for complex line integrals and the fact that this carries over to higher dimensions. So the general setting is there's some complex space, and then on that complex space you're given a holomorphic top form, and then you integrate over a totally real subspace. In that setting, you're allowed to move around the totally real subspace by Cauchy. And that's the way to think. You just push inside the complex space, instead of taking a section which is kind of sort of real in the usual sense, in the sense that you integrating over the Hermitian matrices, you just deform that off the real axis.
In a clever way.
And Cauchy tells you that this is correct, and the answer is still the same after deformation.
But Martin, since you brought this to our attention, I just when reading their paper, I got the impression that it works only for this particular symmetry class.
Correct.
And the effect of this idea, as we know, works for others as well. So still, it's not to be fully disposed of.
But is it clear that it's only working for this
No.
symmetry class, or
So
they have
far.
not produced?
No, they claim that.
and formulate
I have
others?
I have feeling that it's very much okay. I cannot say that it doesn't work for others, but in the way they suggested it, it seemed very much tailored for that class. Although it's very clever choice.
Well, Dyson Malayev is kind of simple. I
Yeah.
understand.
Yeah. Okay. Still, I think this method deserves to be discussed. So we just make this singular value decomposition and introduce these singular values, or in fact something like square root of them, with appropriate phases, as our new integration variables. This μf inherits the property that its modulus is smaller than 1. Otherwise, they're just fine, just complex numbers. And one should recalculate. We remember how to recalculate the measure. One should calculate the Berezinian superdeterminant of corresponding derivatives. It's not totally trivial exercise, but doable by various means. And here, just present the result. You get some factor. And differentials just natural, the rest is just product of all independent differentials. Now, already we can perform integration in these variables, but it's more convenient just instead of these mu's to introduce yet another combination, just two. Okay, it's not that surprising because you see, if you look at these mu's as hyperbolic signs, you may recognize that this will be something like a hyperbolic cosine of doubled angle or something of this sort. So it's very natural, should I say, trigonometric combination. It's just convenient variables, especially because we have these structures naturally arising due to presence of this product of t's with square roots. So for Q itself, then in terms of lambdas, we have a very transparent and convenient parameterizations. These u's and v's, which contain Grassmannians, they are just matrix factors from the left and from the right. So we block diagonalized every block in this supermatrix. So if we just, in fact, you see, in this representation, we just see that it has boson-boson and Fermion-Fermion blocks made. These four variables make boson-boson block of this inner part, and these four Fermion-Fermion block. And these U factors, they are outside. The measure looks like that. You calculate the only object we need for our calculation, supertrace of eta q. You get relatively simple expression, I think, in these variables. Now we can perform this integration explicitly, hopefully.
Sorry, did the u's and the v's drop out by cyclicity, or?
You see, no, they do not drop out because this is these Grassmannians, and they live only inside u's and v's. They do not drop out. If they just literally dropped out, we would be in some trouble, because then there is no Grassmannians in the integrand, and it should be zero then. Fortunately, they do not do this, but they do something. Okay, we will discuss the problems which appear. So this is the integral we'd like to calculate. It's written here explicitly. Now, naively, we just see, okay, for Grassmann variables, we have here bilinear combination. The only term which should contribute is when we expand this exponential, we will have monomial of maximal order, basically, in human language, a product of all them, and which will cancel these differentials and produce non-trivial result. So I happily announce the result. But I'm not that happy, because I immediately see that if I put eta b equal to eta f, I get 0 here, although practically our object was defined in such a way. Okay, I can loosely speaking. Okay, it's in some sense eta minus h, eta f, minus eta f, something of this sort. And precisely the same combination with eta f replaced with eta b in the denominator. So by definition, if you look at the original definition, when we put these etas, basically spectral parameters, in the numerator, in the denominator, equal each other, we must get 1, because we just, this was the property of the object that we introduced. So what goes wrong? But we fortunately know, at least at this stage of the lectures, we should know what goes wrong, because we discussed similar phenomenon on a simple example. We remember that we had this dichotomy 1 equal to 0 already, and we know possible sources. And here sources in some sense similar. Our transformation is singular in a point when this, in fact, this mu b and mu f equal to each other equal to 0. It's also clear from the presence of this measure, but if you do this calculation, you will see that it's in fact singular. In terms of these lambdas, point of singularity is lambda b equal to lambda f equal to 1. And we should take care of this singularity appropriately. We remember how it's possible in principle. There are other, even more clever ways. People know how to deal with it, how to extract contribution from that so-called Yefetov-Wegener anomalous terms. We discussed it on a simple example. Here I just summarize that for these integrals, just recipe is very simple. You should take your integrand, not taking factor from the measure, but just your integrand, and replace lambda b and lambda f by the point which is dangerous point by 1. So we get extra factor, and if you add this extra, it's not extra factor, it's in fact extra term, it just should be added to this contribution, and you then end up with correct and expression which you can also get by using other means from random matrix theory. This is a just correct correlation function which we wanted to calculate. This ends up our exercise. I'm happy that I more or less finished with purely technical parts. I think, okay.
Yeah, so we went through this Yefetov coordinate system and found some singular. Now there were a couple of other coordinate systems around, one of which Martin mentioned. Will that have the singularity problem as well?
Have no idea what will be in this Skvortsov Ivanov parameterization.
Well,
never calculated. Don't think.
Or spherical? Or the Dyson-Maliev one?
Dyson-Maliev.
Doesn't have that.
Doesn't have. It will be immediately
Or
correct.
spherical, right?
Okay.
So you can avoid it by a different coordinate system.
But definitely, because it must not be. It's just artifact of coordinate of singular transformation that we did to be able to perform this integral. But if we know other more clever ways, it should be. Even, for example, if we consider it in original parameterization, it should not be there. I mean, if we are able to perform this integral, it should not be there. It's always obtained as a result of illegitimate, not illegitimate, but singular transformation, which should be appropriately regularized. Okay. So this finishes. So I think by now we have, I hope that we should have pretty good understanding of the nonlinear sigma model at zero-dimensional level. And now, I think in my first lecture I promised that 4.5 lectures will be on this, and then 1.5 will be on something related to localization. And I think that I almost kept my promise. It's very close to middle of the lecture. And now I consider using the knowledge that we have now, I consider how we apply all this to extract some information about disordered systems. the idea goes back to Wagner and has the name of Wagner n-orbital model. And this is the following, I mean, inherently simple, but on the other hand, profound construction. Namely, consider lattice. We in studying disordered systems many times, I mean, in Tom's lectures, in Pasteur's lectures, we are especially in Tom's lectures, we're interested in kind of lattice Hamiltonians with disorder. So let us provide yet another kind of lattice Hamiltonian with disorder, which won't be built up on the microscopic level using natural object like lattice Laplacian, but nevertheless we'll have something of similar sort which will allow effectively some waves or wave functions propagate across our lattice, and we can study whether they really do propagate or they just localized or whatever. You see, random matrix example was very nice, but on the other hand, it's simple. It does not have any special structure in it. Because of this rotational invariance in its basis, it does not have features necessary to study interesting phenomena like localization, and which are all basis dependent in a sense. So let us really consider lattice with and associate with each side of this lattice. So we have lattice lambda with just cardinality of lambda, just number of sides in this lattice, these modulus of lambda, cardinality of lambda. Just for simplicity of drawing it in d equal 2, here it's d equal 1, just chain. In d equal 3 will be, say, kind of cube, and so on. But with each side of this lattice, we associate, in some sense, inner or internal structure, which is represented by individually vector space of dimension capital N, very akin to this internal structure, to our, basically, we will see that on-site structure will be identical to GUE structure we already exploited. And, but we associate such a vector space with each side of this lattice. So our total vector space is just direct sum of all these vector spaces. It's convenient to think of this of linear Hermitian operators acting on this vector space as basically square Hermitian matrices of size number of sides in the lattice times number of dimension of these internal spaces associated with each side. So they will be basically written in this block structure, where each block is by itself is matrix of size n by n. Diagonal blocks are Hermitian matrices, and off-diagonal blocks are just general matrices with complex entries. Let us further assume the following, that the entries on the diagonal are taken independently. They are independent and identically distributed matrices, taken individually from this GUE. So they will have just GUE properties. Moreover, although it's not necessary, but it will be very convenient for us, we can consider it on arbitrary structure of the matrix here. But to reflect special structure, let us assume that matrices H with indices I not equal to J of diagonal blocks, they are non-zero only if sides I and J they are nearest neighbors in our lattice. In one-dimensional setting, it will be just basically block 3 diagonal matrix. In high-dimensional setting, I cannot so simply draw this in form of the matrix, but it's completely clear what I mean by saying that only those blocks in this matrix are non-zero, which correspond where indices I and J are just nearest neighbors on my lattice. Okay, now we said that diagonal blocks are just GUEs, not so we in fact for these 4.5 lectures we just studied one side in its internal structure. Enough by now. what about off-diagonal blocks? For purposes of being able to perform some explicit evaluation of the interesting objects, we also assume them to be Gaussian, and although they are not Hermitian, so this is the measure associated with each of diagonal blocks. We just have them Gaussian. They are all independent. Real and imaginary parts of all entries are independent, identically distributed, but their variance we will choose in a different way with respect to the variance for diagonal blocks. I hope you remember, if not, I just recall you, that typical variance of entry of GUE matrix is 1 over n. If you just take its Hij of given entry of GUE matrix, you multiply it with its complex conjugate, you evaluate expectation value, it's 1 over n. Here you see that I choose these variances be parametrically smaller. It's scaled 1 over n squared with some constant, positive constant, which I called v squared, and I assume that this v is finite when n tends to infinity. We shall see that this is precisely the scaling which allows a non-trivial limit n to infinity to end up with something interesting, with nonlinear sigma model on the lattice. So, but just please remember that in this sense, off-diagonal blocks fluctuate fluctuations much smaller in magnitude, parametrically smaller. They by factor 1 over n smaller. Still, to average over Gaussian distribution is very easy. So, if we have any two matrices A and B, and we have one of these off-diagonal blocks, how to average over exponential of something linear in H for diagonal blocks, we know probably by heart because I used it so many times. But similar formula, of course, exists for off-diagonal blocks. It's just practically, hope you remember, for Hermitian, when we had Hermitian matrices, we had just trace of HA, and here we have minus 1 over 2n trace of A squared. Here it's similar construction, but we, of course, simultaneously should average over H and its complex, its Hermitian conjugate, because they are related by conjugation. And the result is this. Please verify it. It's again straightforward Gaussian integral. And Wegener realized that these type of models can be used to reproduce most conspicuous and important salient features of localization for more standard models like Laplacian plus random potential on a lattice. And let us discuss what should be expected from that point of view. So here just small recapitulation. I think we've heard it from Tom, and we will hear things from Tom. Here's just a complementary picture, just reminding few simple things. So we hope to be able to describe what? To describe a particle in physical terms, just particle, quantum particle, which is scattered by random potential, which we physicists think is probably generated by static impurities working for just inducing scattering. So our electron, say, moves in the classical, it will be just randomly scattered from this static potential or from these impurities. And there are two important scales here. Just size of our lattice, if we speak about lattice, or our sample is its our volume, typical size, which is big and eventually will be set to infinity. And there is another typical length scale, which is so-called mean free path. I think it also appeared in Tom's lectures, that basically typical should be understood as typical distance which particle travels without being much scattered. And if we believe, as Tom again demonstrated, it's a very non-trivial thing to even classically to show what happens here. But if we not rigorous mathematicians but naive physicists, we believe that we understand that there will be random, a longer time will be just random change of direction, and it's just will be random diffusion of this particle. Then it's natural to expect that classically typical displacement of this particle will grow linearly with t, where coefficient, at least definitely I have in mind asymptotically, not on smaller time scale. And this d is related with velocity of this particle and typical distance which it comes without scattering. So it's very simple exercise that if we assume this picture that d should be just given by product of velocity times this mean free path. I keep here this index f because I, of course, think about electrons at Fermi level, as we've heard today. So it's Fermi velocity in some sense. But so far it was purely classical picture. So basically our goal is to understand whether at all, and if to which extent, quantum interference effects, after all, our particles are quantum particles, therefore they are waves propagating, interfering, and how this interference interferes with classical diffusion. I mean, whether it, we think that probably under some circumstances it could be an important mechanism which hinders this diffusion. Okay, now again a reminder of a few things that in various incarnations were already discussed. I think in Pasteur lecture, and I think also Tom somehow invoked this thing. Basically, we are interested in quantum evolution. So we'd like to know probability, quantum mechanical probability to arrive after period of time t from starting point x0 to point x. And in terms of quantum mechanics, it's just given by evolution matrix elements, modulus square of matrix elements of evolution operator, this object. Now, we, of course, here I mean, my drawing was about large but finite system, and sometimes I will switch from finite to infinite and backwards, but it's always very big. So deep inside, or literally speaking in infinite size limit, expectation or average of this quantum mechanical probability, which is of course random, if our potential is random, it's random quantity depending on realization of your disorder, then its expectation is translational invariant. It itself, this quantity, is not translational invariant, of course. At every realization, it depends on two positions, because there is a particular pattern of impurities in between these positions. But after averaging in infinite size limit, it must depend only on distance between the points, so be translational and rotationally, in fact, invariant. If I was, yes, an infinite sample. Now, if we know the probability to this probability, then it's simple task to define a quantity which we expect to be diffusion constant. It's just, in fact, it's definition. I think also Tom used very similar, if not identical, definition. So you just should calculate expectation of fx squared over this probability density, and coefficient, just extract linear coefficient if it exists, if it's linear, if this behavior is linear, and means dividing by t and allow t tending to infinity. Just for generality, it's convention. I introduced here dimensionality. It's common thing that if you have change in dimensionality to introduce d here. Now, okay, we have this object. It's expressed in terms of evolution operator. But in order to calculate such thing, it turns out that it's most easily expressed in terms of kind of okay, it's limiting behavior of something depending on t. It's known to be extractable from Laplace transform of the corresponding quantity. So that's what is done here. I just take Laplace transform. Since I have modulus square, I will have Laplace transform of a product of objects. Therefore, it will amount to the structure which is shown here. So basically, it's easy to understand that we need to know basically matrix elements of this evolution operator in NG representation, in Fourier transformed representation. So let's introduce the most important quantity for us. It's just expectation value of product of advanced, we call it advanced and retarded green functions, which are nothing else as our familiar object, which we are happy to see again. It's resolvent in position representation, where z, here it's not written how z is related with e, but basically by z I mean this. So this will be z bar then. So you see that it was not so stupid to consider z's and z bars just conjugated, and that's it. They really come in objects of this sort. So it's again a backward justification of the thing that I considered that time. It's related. My choice was related to this. So we need to know this disorder average. It's basically the same kernel, but in after Fourier or Laplace transforming. It depends. After Fourier transforming, actually, you can play with it. And I do not have time to prove it, but I think it's in fact really simple exercise of Laplace transform. Take this formula, understand how this is related to this. Again, it's Laplace transform of this, and extract leading behavior when t tends to infinity, and you get to the following expression. You get to expression of this constant d, which we expect to play the role of quantum diffusion constant, in terms of integral over energies of second derivative of Fourier transformed in space, this object k. You see, important thing. Here, disordered average is applied. Therefore, this correlation function of two green functions, it's dependent again only on, in a large volume limit, only on separation between variables. So it's very natural step to do Fourier transforming in real space. So we do it. We introduce conjugate variable, in some sense, momentum, if you'd like. And in terms of this, after relatively simple manipulation, you extract diffusion constant as a limit when epsilon goes to 0, where epsilon is imaginary part of energy. So this is all reminiscent of what we did in our exercises. We all the time considered imaginary part of our resolvents or spectral determinants related to resolvents in the end of the day go to 0, go to the real, go spectral parameter to the real axis. You see, this is really very important thing, and this is, in fact, this epsilon to 0 is another incarnation. It's just, if you'd like, dual way, or better to say, a way of performing this t to infinity limit. If you'd like to extract t to infinity behavior, you need to extract epsilon to 0 behavior.
Or maybe we could also say, which is something I will be using, that t is like 1 over epsilon.
If you'd like.
If you don't want to go to infinite time, but some large.
Then keep epsilon of this sort.
T is roughly 1 over epsilon.
Yes, I agree completely. But I think that this shows this duality between epsilon and t quite clearly. And also maybe, again, explains why we were so interested and why some non-trivial behavior appears usually only in this epsilon to 0 limit.
Maybe one extra remark. Tom, in his lectures, occasionally, in particular when he refers to the continuum, put in a projection which removed eigenstates outside some definite energy interval.
Here I just integrate
You
over.
integrate over everything. That's okay if the spectral type is everywhere the same, if it's everywhere AC or everywhere per point, you don't care.
Or will
If it's
contribute.
mixed,
It's only
you have
this
some
contributes.
region of localized states and some extended states. I don't think you want to integrate over all energies.
Effectively, I also will
Everyone
be
in a
projecting
single
out.
point,
Yes.
you'd like to have more resolution.
I will consider then, I will introduce, I think I will just now introduce the notion, in fact, of energy-dependent diffusion constant, which in fact projects it to a point, to a point in the spectrum. Basically, okay, now, okay, few words. It's nice that Martin started to discuss it, because this is practically what I'd like to do. Now, if the energy is in the part of the spectrum which we believe to correspond to extended states, which eventually diffuse to infinity, then we expect that basically this probability density is nothing else as at large time it's diffusion. It's diffusion kernel. So it allows immediately to write down what we expect, what will be the corresponding form of k tilde, of Fourier transformed version of it. And this will be what is known as diffusion kernel. Just again, very simple exercise. You will see that in this case, you see, we need q to 0 because of because here this q to 0 limit is needed to produce diffusion constant, and it's just a way of extracting corresponding diffusion constant. One can discuss it on a deeper level, but anyway. So we're interested in the limit of smaller. Yes.
Have you done already the limit on n to infinity?
Subconsciously. it's subtle thing. No, okay.
Just
No, okay, I didn't. Okay.
no, yeah.
This I made this vague remark. I made it deliberately that I will change without much caution from a picture when I have really infinite sample already thermodynamic limit and then everything translational invariant and all that, to the limit when I have finite sample and discrete.
No, I'm not about finite. I'm about number of orbitals.
Ah, number of orbitals. You see, this is a okay. I misunderstood you. I
How
misunderstood.
does your epsilon depend on n?
Important thing. 1 over n. It's in the same scaling as. It must be the same scaling as in GUE. I reiterate all the time that in order to have something relevant, because this is this n already, although we use it later on just to calculate something, to reduce it really to lattice nonlinear sigma model, it's in kind of auxiliary variable. So scaling with capital N is always like in GUE. It's 1 over n. But there is it's not thermodynamic limit. Thermodynamic limit is really lambda to infinity.
No, I understand, but I'm mostly concerned with.
It's 1 over n, definitely. Without this, if you just keep epsilon fixed and n tends to infinity, this will be kind of stupid limit. You won't get anything interesting. You really should.
Yeah.
You won't get. You will get only the localization and triviality.
What Wegner did in his
No.
paper. So
No, I don't think so.
No, I think so.
Yeah,
But
Wigner
doesn't
did
matter.
not take this limit that you're describing, but never mind. He defined the model, and then later people said, let's take a certain limit, and then the model will have its will be most interesting.
But we understand what this limit must be.
Phenomena that are supported by
Yeah.
it.
Even if such an ingenious person as Wegner was not careful enough at that point, everybody more or less understands what should be this limit. I mean, otherwise, you just may check, you will get triviality. Also on the level of GUE, you will get triviality.
Well, that's what Wigner showed in his paper, that you get something trivial.
Ah, so he just didn't, okay. Okay,
Always have diffusion.
then thank you, Leonid. In fact, I was not aware of this fact.
You just have to go and read the paper.
Okay, I will do. But I think that we understand well how the limit should be taken to produce meaningful results. Okay, it's
Well, it's always meaningful, but this is particularly interesting. In this way of taking the limit, you still have the possibility for localized states.
yes, yes. So you may have such non-trivial. You see why we like nonlinear sigma model, because we believe, although it's not mathematically verified yet, but there are all reasons to believe that this is object which contains in it all essential universal features associated with Anderson transition. It has two phases. It has non-trivial transition with presumably, and we believe, and abundant evidence, multifractal structure at the transition point. So it's really, it is a theory in some sense of Anderson localization. Appropriate, all relevant degrees of freedom are taken into account.
And did everybody found the mobility edge in that model?
What do you mean? Okay, we will discuss it. Perturbatively in a sense of renormalization group, or there are reasons to believe that strong reasons to believe on Berta lattice in sense, yes, but in realistic dimension, no. I will say that there is no proof of this.
But there's sufficient numerics, I guess. On
Yes, but yeah, numerics.
Well,
Sufficient.
numerics is not done in the sigma model.
Yes.
Oh.
Oh, no.
Certainly
Yeah,
not
I agree. No,
large and
no,
limited.
no.
Yeah, okay, sure.
Yes. No doubts about the doubt were expressed about adequacy of this model that we obtained for describing Anderson transition. I think that the consensus is that it is adequate, or adequate in positive sense. I mean, it describes all necessary ingredients. It has all necessary ingredients. Just, I do not remember, maybe it already appeared in Tom's lectures, that when we, what this form of Q-dependence means in real space, it means that when epsilon goes to 0, basically your, this product of two green functions decays as a power law d minus 2 for d larger than 2. And on the other hand, if we are in the range corresponding to exponentially localized states, one can show by simple consideration that the behavior which we expect should be quite different. It should be singular with epsilon in this limit, and the corresponding residue should be just exponential, show exponential decay with characteristic length with this localization length. And in my formulation, or in my definition of D, how I introduced it, in fact, it's integral over all energies of these DEs which feature here, but the most interesting object will be to study D at given E by the reasons Martin mentioned and Tom did.
What happens to D in this?
Where? Here,
Because
D0.
Is
Yeah.
absolute, and in this X should be a very large X, or it's at any scale?
Yes, it's asymptotic behavior, of course. It's asymptotic, much large. The only relevant scale is Xi, depending on energy. It diverges when you approach, presumably, localization edge, transition point. And Xi should be kept, in order for this to be valid, X should be kept much larger than Xi. So that's it.
Is there any relation between this localization length and the amount of disorder?
Yes, okay. In a sense, disorder controls your position of your mobility age, but if you just fix your energy and increase disorder further and further and further, then at one point you will come, mobility age comes to this point, and further will be your localization length will be shrinking beyond this. So this will be the first situation when your diffusion constant vanishes and finite localization length sets up. And with further increase of disorder, Xi will be shrinking. That's it. So the larger is disorder, the more localized are states. So, I mean, it's qualitative picture, but I think it's correct, more or less. Okay, so now what is the object which we should consider, or which is convenient to consider in our, I maybe return back this picture of our system on the lattice, just lattice. So you see, we just demonstrated, we just discussed that a product of two Green's functions at complex conjugate energies at 2 points x and x naught really represent the object which knows about diffusion and about various phases and all that. So what is analog, natural analog of this for a Wagner model? You see, if in usual lattice structure, we just should consider element of the resolvent between point I and j and multiply it with its complex conjugate and average. In order to preserve some nice invariance which is inherent in this model. In fact, this model, you see, it's sometimes called gauge invariant model because it's, you see, all these blocks, they are invariant in distribution with respect to multiplication with unitary matrices of dimension n. For GUE, we know this. I mean, it's also here we just made such a choice that there is this, I would say, local group of invariants. Of course, we can still consider literally the objects, just a green function from one of internal states, one of n states living inside this site I and another state, but it's really too microscopic for our goals because really we do not care much on this resolution of things inside this blob which we parameterize by this matrix. We are not very much interested. So what we should do, we should effectively sum over all internal structure in one side, sum over all internal structure in different side, and consider this type of object. This is precisely what is written here in a little bit more formal term. We just introduced orthogonal projector on the linear subspace spanned by one of the sides of site I. And then this is precisely the object which we'd like to calculate. It's basically our resolvent, resolvent taken at conjugate value of a spectral parameter. And these projectors just ensure that you sum up over all pairs of this internal structure between site I, say, and site J. So this is a very natural analog of and also with nice invariance, keeping a nice invariant structure of the original Wagner model. Okay, I think probably this is a natural place to stop, and I'll continue discussion and derivation of associated lattice versions of the linear sigma model, and hopefully discussion of the physics behind it, some physics behind it, not all physics, next time. This will be my last final lecture. Hopefully. Yes, please.
For this type of model, is it proven that there is no subdiffusive evolution?
No, I don't think that there is any proof of this sort. No, it's still there. I don't think I should ask. We should ask Tom whether there are and which sort of rigorous results exist for this model. I don't think that many.
Well, I think the statements I made yesterday about subdiffusion and subballistic motion
I don't think it
would apply here too.
In general, will apply.
Yeah, it's fairly general.
Okay.
But that doesn't, so you will not have subdiffusion without having localization in 2 dimensions.
Yes, it's what is natural.
In 3 dimensions, then you could get. I mean, we can't rule out subdiffusion. We can't even rule out superdiffusion, which is an embarrassing thing.
No, I think the short answer is just to reiterate what I said to Lenin, that general consensus of physicists working in this model, and I think hopefully of bunch of mathematicians thinking about it, that is really this model will have all natural features of the Anderson transition and won't have pathologies which some other models might have. So it's really a sort of minimal model, of Anderson transition.
Would the interpretation be correct that you don't have a bit in this Wagner Hamiltonian which corresponds to the Laplacian? The Laplacian is in principle a translation, and there
I can tell you
random hopping between these orbitals.
Okay. Basically, what this model does, I can tell you now because I don't think that I will discuss. You see, in a usual, suppose you have a Laplacian on the lattice plus disordered potential. Really, the model we'd like to understand. the natural objects to start with, and in fact, all first calculations are for this model. You just take not product of two resolvents, but just average one resolvent at two distant or two different points. Then, for realistic physical model on a lattice or in a continuum, whatever, this will decay exponentially with some typical length, which is in a sense, for the simplest model, basically this is mean free path. So basically, physics is very simple. It's oscillate this Fermi, at the Fermi level. There are high oscillations, and they are damped by this scattering. So you have just. It's pretty uninteresting. This decay has nothing to do with localization. It's a very simple phenomenon. So what Wagner model does, it gets rid of this irrelevant microscopic scale. We should, in fact, we shall see that interpreting this some results of this model, we should have in mind mean free path. It's a very important parameter, in fact. I will permanently again hop between this picture of particle scattering and results of non-linear model. But literally speaking, mean free path is just set to 0 here. All average of green functions between 2 points, not product of the green functions with opposite sign of imaginary part, will be local. They will be just concentrated on one side of the lattice.
But maybe I can try another answer. This is a quantum mechanical model. When n is large, it is a very good approximation to think of it for finite time in terms of classical evolution. So you can write almost closed, not quite, but becomes closed. It's ever more closed as n grows up to infinity. You can write an almost closed equation for the square of the wave function. And that evolves according to the lattice Laplacian. So the associated classical limit is governed by the Laplacian.
You mean diffusion essentially? Yes.
Which, of course, the evolution generated by Laplacian is diffusion. Everybody knows that. Okay?
But it's slightly different.
But this model has quantum corrections,
Yes.
which grow. As t becomes large, they take over, and well, it depends on
We will discuss it later.
on the strength. So,
Yeah.
but in a parameter range, this model has localization. It's not a mathematical theorem, but
fast.
I still try to promise Tom to find the reference to Fyodorov, where he makes a sound argument that this is really the case.
Yeah. But intuitively, it's clear.
But it's not mathematical in the sense that it is proven, but what is the ideology? That if I'll take the epsilon of the order 1 over n, then I'm going to see everything, localized,
Yes.
localized,
Yes.
mobility edge, everything.
Yes.
Yes.
Yes. This is definitely must be kept like this. Beyond that, it's non-trivial object to be studied. Non-perturbatively, we shall see not that many results exist, but perturbatively some machinery
Perturbative
can.
in which parameter? 1 over n or
Okay, we shall see. In effect, in effective large diffusion constant, if you'd like.
The large, I would just make a comment. The block size that you're using, the n, the capital N, not the lattice, but the block.
But this is not parameter. It will be already exhausted. We will use it to derive nonlinear sigma model. After that, we won't have this parameter at our disposal. No. Unfortunately. Yes.
There are regimes in which you can set it up a little differently, and then the block size becomes equivalent.
Okay, I could believe it. But still, I think you needed to arrive to the nonlinear sigma model. To analyze it, you need a large diffusion constant in some to set up perturbation theory.
So the fact that we're doing this at all seems to imply that the analysis we've gone through previously will not work when H has a lattice form.
You mean yes? What means literally expectation value of resolvents will be, of course, very different from GUE case.
Yeah.
Yes.
Can you describe why we can't use the techniques we've
No,
developed?
we will be using the same techniques, but you see, okay, it's very simple. So far, we studied just a single side of this lattice. It was useful exercise to introduce techniques, but it's completely devoid of special structure where localization sets up. So we need something to to have room to localize. And this our lattice structure will provide.
I mean, if I just try naively to take a Hamiltonian that has a lattice structure and apply these techniques to it,
Yes.
something's going to go wrong.
No, you will arrive, if you do it correct, we will do it next, we won't do it.
I don't mean a GUE, I mean if it's just the Laplacian on the left.
Ah, you mean really, really,
Yeah, so something's
okay.
going to go wrong.
Just some, no, it's not going, no. Oh yes, if you'd like. Some steps, some steps will be not that controllable. You won't have really very good control, or at least people do not know how to make it really control saddle point approximation, all that. There is some understanding what controls it. Physically, it's well defined and people use it all the time and derive it. But literally, to derive it step by step, we can do it on this level because we have a controllable parameter n, this number of orbitals. But it's much less clear-cut case.
In short, you can still do it, but it's useless. Yeah. You know, you can do anything in the world, but you only do it if it brings you forward, if it helps you. So if you use the method in just any setting, you get an integral over these supermatrices. Yeah. Gosh, you made the problem more complicated than the problem was to begin with. In the GUE, you didn't make it more complicated. We saw that you could calculate everything to the n, so obviously it was useful. In the case of the n-orbital model, it is still good because in the transformed or in the reduced formulation, you have one supermatrix for every site. And you now have to, in a sense, solve the in view of David Bridges' lectures, we're in a statistical mechanical setting where we have a renormalization group, and we can hope to learn something about this coupled system of supermatrices. It's still, as we heard, there are no theorems, but we feel that we understand what's going on. We can compute perturbatively the renormalization group. I mean, Andreas Ludwig showed, I mean, the results that he showed apply to this model. It falls in this class where you predict the renormalization group flow based on curvature, Ricci curvature, Riemann invariance, constructed from Riemann tensor. So we feel that we make progress using the method in that setting. But if you ask what happens in the most general, I have to say, don't do it. You're just making something complicated even much more complicated.
So I end up with an integral over a manifold I know nothing about.
Yes.
You don't have a good control of what is relevant there, what is not. Physicists understand, in fact, what is relevant, but to make it. Yes.
So, I mean, in a way, this large matrix that you introduced at each site has given you another parameter, which helps because you can do saddle point methods.
This internal structure.
Right.
This was precisely the idea, yes.
So, you know, it's a kind of very grand version of, for example, replacing the Ising model by the large n limit, right?
But you see, locally,
yes,
it's important thing.
Yes, no, I understand that.
It's very important to keep.
Does the n, does the, not the capital N, but the size.
Lambda.
The lambda, yeah. No, I do mean the capital N.
Oh,
Does
okay.
the capital N, is there in fact a physical interpretation of that parameter?
I would say, okay, it's not literally, but it keeps, it freezes out by saddle point approximation some irrelevant degrees of freedom which have nothing to do with localization. In the same way as this gauge invariant structure, as I mentioned, just sets this irrelevant scale mean free path, in some sense irrelevant for the localization purposes, to 0 from the outset. So it makes this a good job. But literally...
I can give a more physical answer. It's called granular systems.
Oh, okay.
In fact,
okay, in this sense, yes.
In the laboratory, they are under active study by real experimentalists. So
You can build it.
the metal or insulator is not a homogeneous system. It consists of boxes, real thing, grains, and they're separated by grain boundaries. And the transition across a grain boundary is much, much slower. It takes much longer. It's kind of a tunneling process. So also the scaling that the off-diagonal, the variances of the off-diagonal elements are much smaller. In fact, by 1 over n, it makes complete sense in that physical setting.
Yes, you can do it.
So you say each grain you're going to model by G.
Yeah, I understand.
if you believe in this.
Relaxation and the dynamics inside the grain is fast. There are no barriers. The electron can explore the available phase space very quickly. So it is reasonable to model that by PE. On the other hand, to go from one grain to a neighboring grain takes tunneling through a barrier. It takes much longer. So you reduce the strength for this. And now, by keeping the grain size, the product of the grain size, times the mean square tunneling matrix, by keeping that fixed, fixing the physics, you're then allowed to increase the grain size, the dimension of the number of states on a grain, all the way to infinity, without changing the large-scale physics. Because by the golden rule, what matters is the product of the transition matrix element square times the density of states. So you're scaling up the density of states, reducing the transition matrix element in such a way that the transition rate, the rate for particles to go from one grain to the next, is kept fixed. It's a perfectly physical limit. Leonid keeps asking about it, but it is perfect.
One can also...
Nothing you can quibble about it. And we should expect all the phenomena of Anderson localization to be present. Although we don't have a theorem proving it, but you know, everybody in their right mind will say this is a great model to study.
I have one other comment to add, maybe not so much for myself, but for other people in terms of this renormalization group. Am I correct in thinking that if you tried to do the renormalization group on the original model without this parameter n, it would evolve away from things you understand like Gaussian models, and it would evolve into something that you can't control at all because coupling constants become large.
Right.
But if you bring this capital N in, it's rather like in the 5/4 field theory, you bring a putative fixed point that you don't understand close enough that you can still work within the renormalization group and get to this other region.
Yeah, well, you see, the metallic state, which we expect in 3 dimensions, in this model is supposed to be a Gaussian fixed point where the phenomena that you described to us yesterday morning takes place.
Yes.
We don't have a reflection positive model. We don't have infrared bounds, so we cannot use the classic proof of Fröhlich, Simon, and Spencer. But morally, the same thing is happening. And we're looking for, and in some simple cases, we now have a substitute. Tom and Margarita have worked out a substitute showing it. In a thermodynamic limit, you flow to a Gaussian type.
Can one approach the latest model just in the sense of multi-scale analysis? You can dig bigger boxes where n capital of units live, and then you consider just interaction between them. Is it applicable in this sense?
Have no good
If you
understanding.
just look at the same lattice but from a bigger scale.
In some sense, it's a renormalization group idea, yes. What you do, but okay, I don't know if you can do this literally, but definitely renormalization groups are applicable on the level of nonlinear sigma model. I won't discuss them much, but just mention that what they predict. Let's see.
I would just like to make one general comment. I know many people here are interested in random matrices and eigenvalue statistics and this kind of thing. And of course, as I've tried to point out, we don't know as much about these things as we'd like to once you move away from Gaussian or unitary ensembles. But this formalism that you've described here gives you a very coherent picture of why this should be universal, it seems to me. And well, maybe you haven't quite gotten to that point yet, but the saddle dominates the physics as long as you stay away from the mobility edge and as long as you don't have too much fluctuation. That means you have to be in 3 dimensions. So universality becomes really the universality of some saddle point or some mean field theory.
I would say that yes, so that already this nonlinear sigma model which we are going to derive is pretty universal. It has a coupling constant in it, and then it evolves according to renormalization group
And then,
somewhere.
then the universality becomes fairly transparent because the saddle point is really only depends upon symmetries in the system, essentially.
In this sense, it's universal. I mean, universal by very construction, but it's the case for all nonlinear sigma models. I mean,
Yeah,
that
that's
they capture.
very important philosophy. We wish we could translate it into theorems.
Well,
It's a very important philosophy, which you don't see from orthogonal polynomials.
No,
You have to
completely-
somehow work
completely
hard to get some
mysterious.
asymptotics.
Not
You don't
at all.
really see, or at least I don't see. I know that this technology and Riemann Hilbert also, I mean, it also reduces it to a saddle point analysis at the end of the day, but it's much less transparent exactly what that is and how you approach it and how general it is, how much you can deform it into other regions of the parameter space of all possible Hamiltonians.
And it gives
Anyway, I
nothing
think people
for-
want to
for
be keeping
non-direct.
Yes.
everybody hungry. Sorry for indulging in our. Have a good lunch.